Now, a subdivision of neutron stars are pulsar stars. Pulsars were actually discovered by Jocelyn Bell back in 1967, and she found these pulsars, of radio waves. She's an astronomer looking into space, and she gets a radio wave, and then another radio wave, and then another radio wave, and they are exactly 1.34 seconds away from each other. So one radio wave comes through, 1.34 seconds later we get another one, 1.34 seconds later we get another one, and on and on and on. And at first they thought they were little green men, because this was such time specific that, well, it can't be something that just happens by nature. It has to be someone controlling it. Turns out, no, it's just a pulsar. We'll talk about the model next on how they work exactly, but we know of 1,500 pulsars. 1,500. The shape is different, like the pulse shape, what's coming through. The period, the time is different. Can be milliseconds to seconds, and they're very natural, like stable clocks. Just whatever their rate is, they happen at that rate all the time. So Hewish was actually Bell's graduate advisor. So he came up with this pulsar model. And this is kind of it. So you've got the neutron star, okay, and you have the magnetic field. And then what's happening is you're getting these beams of radiation from the poles of the neutron star. And that's what we're detecting. So we're detecting this beam of radiation, and as the neutron star spins around, the radiation beam will spin around with it, right? So we'll get the beam and then we won't, and then we'll get the beam and then we won't. So these two beams are called hotspots. There's two of them, one on each pole. Right. They are linked to both the surface and the EM field, and they're constantly giving off radiation. Right. It's basically charged particles emitting radiation, and they're being accelerated by the fact that the magnetic field in the surface is spinning so much. Okay, so pulsars give off the radiation at the hotspots at a steady rate. They're constantly giving off this radiation. And so when the radiation hits us, now I guess that's not the proper word because we don't want it to hit us. If it was too close to us, well, it would be like being attacked by a machine gun of radiation, and it would just fry everything, and that would not be good for the human race. But if it comes around and we're able to detect it, how about that? We're able to detect it, and then we're not able to detect it, and that's why Jocelyn Bell saw like 0.1 seconds and then nothing for over a second, because it's kind of like a lighthouse. It's actually a pretty good analogy for the lighthouse, right? If you're out to sea and you can see the light and then you can't. It's not like it brightens and then dims as it goes away. It's there or it's not. Right? And so that's a really good analogy for these pulsars. The radiation is there or it's not. So some pulsars can actually come from inside a supernova. The speed, the direction of the expanding gas can actually be traced back to this pulsar. So if we can detect the pulsar and we know the information about the pulsar, we can figure out the speed and the direction that the supernova is going. So the pulsar that Jocelyn Bell found was actually a radio wave pulsar. It doesn't have to be a radio wave pulsar. It can be any type of wave pulsar. Okay, X-ray, visible, radio, gamma, whatnot. And so you can see pictures here of pulsars. So along the top, or the top picture, I guess, you can't really see anything. You've got this bottom star, but then the top star, nothing, nothing, bright. And then dims, and then bright, and then nothing, nothing, nothing. So this 0.24 seconds is the radiation from the pulsar. The rest of the time you can't even see that it's there. Now, thanks to Doppler, we're able to figure out that pulsars are actually moving very fast through space. Right? Stars move through space, so why not pulsars? And they're actually going pretty darn fast. And what we think is that because of the supernova, for every action there's an equal and opposite reaction. So the supernova is going one way, the neutron star is going the other way. Now I say neutron star, could be a pulsar, right? Pulsar is a neutron star.
A pulsar is a rapidly spinning neutron star, which is the small, incredibly dense remnant of a much more massive star. A teaspoon of matter from a neutron star weighs as much as Mount Everest, and a neutron star is so compact that a ball about 15 miles across contains more matter than our sun. Neutron stars spin between 7 and 40,000 times a minute and form with incredibly strong magnetic fields. Rapid spin and intense magnetic fields drive powerful beams of electromagnetic radiation, including gamma rays. As the pulsar rotates, these beams sweep the sky like a lighthouse. To a distant observer, the pulsar appears to blink on and off. Pulsars slow down as they age, but some of the oldest pulsars spin hundreds of times a second. Each of these millisecond pulsars orbits a normal star. Over time, the impact of gas pulled from the normal star has spun the pulsar up to incredible speeds. This accretion may be the cause of their weaker magnetic fields. Despite this, these pulsars also emit gamma rays.
So all pulsars are neutron stars, but not all neutron stars are pulsars. And this is just kind of strange. So for every one neutron star found in our galaxy, we think that there are hundreds of thousands of them that we can't see. And we know of 1,500 pulsars. Never mind neutron stars. That's insane. Now, why can't we see them? Well, probably some of them we just don't get the radiation. Or some have stopped giving off radiation. So really hard to detect if you're not giving off anything. Now, another remarkable thing is that the theory of stellar evolution, right, how stars develop, the theory that we have actually matches up with what we can see in a pulsar. Right, there's a supernova explosion, the neutron stars are left afterward, and these radiation beams come from the young neutron stars. And the theory matches up with what we can actually detect and see.